Okay, so good afternoon, everyone. First of all, thanks for Wade about the very good introductions about quantum mechanics. And what I'm going to talk about is really utilizing quantum mechanics in a lot of different applications. So first of all, if you look at the title, basically this is about more like applications of quantum materials or so-called nanomaterials in applications. And today I will go over two very important applications, and I will also go over some more other applications. The first one is how we're utilizing the nanomaterials or quantum materials or the concept of quantum mechanics into nanoscale transistors. Actually, we have given a very brief overview of transistor array, and also how we're utilizing even the nanotechnology into energy harvesting, or even later applications like in biomedical applications. So also, on one hand, I'm representing CTU since I'm from computer science engineering, and on the other hand, I'm also a member from the Hong Kong Young Academic Sciences. So actually, this association, we have altogether 40-some members right now, and all are pretty much faculty members in all the different universities in Hong Kong. So one of the key vision is trying to promote the science and technology, because we do feel this is very, very important for our next generation in Hong Kong. So for the past 10, 15 years, I have been working on nanomaterials for very day and night. And basically, what are the quantum materials or nanomaterials? From quantum mechanical background, from physics background, we have already given a very detailed overview. And from material science background, because I'm a material scientist, how we look at the problem for the material point of view. And also, why we want to develop nanoscale materials, why this is important. And most important is how we fabricate those materials. And for the application part, as I mentioned, we will introduce the use of nanomaterials in transistors, and also energy harvesting, and also some other applications. So, nano. So if you know about this term, so basically this is a unit of length. So this is 10 to the power 9 meter. Okay? So if you think how large is 1 nano, or how long is 1 nano, you can think about this is like 10 hydrogen atoms connected in a chain, and this is considered 1 nano. So it's really that small. So if you think about concept-wise how we imagine an object like this, then you can think about a nano concept is how a object sitting, one nanometer large object sitting on a table tennis ball is comparable to how a table tennis ball sitting on Earth. So this is that kind of comparison. So you can see it's really that small for 1 nano. And if you talk about human hair, this is about 60 to 80 thousandths of nanometer in the diameter. So you can see it's way, 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 way smaller than 1 human hair. So this is really a small quantity. And if you also talk about the human height, like Uncle Jordan, about 2 meters tall for saying, then it's 2 billion of nanometer tall. And then you think about a nail head, it's about 1 million nanometer for the nail head. And all the way down to hydrogen atom is about 0.1 nanometer for the diameter, roughly speaking. Okay? So that's why I'm saying if you connect 10 hydrogen atoms together in a chain, that is 1 nanometer. So you can think about this is this small. And how we can really fabricate this small dimensions, and how we really utilize that small dimension in materials for different applications. So, advance on nanotechnology, so back in the quantum mechanics fathers, and actually one of the fathers is Richard Feynman. And he is the Nobel Prize winner in physics back in 1965. And so he actually has a speech during his lecture. So he mentioned the principles of physics, as far as I can see, do not speak against the possibility of manipulating things atom by atoms. Okay? So if we can really manipulate the things atom by atoms, like what chemists do, because they put molecules together to make useful larger molecules for applications, right? So this is really how importantly can virtualize the world if we can manipulate the length scale atom by atom in the nano dimensions. So how we can fabricate those nanomaterials? So basically, we have two major schemes. So the most useful or typical one is what we so-called the top-down approach. So this is what we call subtractive approach, because we start with a very large pieces, and then we try to subtract the material from the top surface. So it's a subtractive approach. So we basically start from large dimensions and take in, and go smaller and smaller. So this is called top-down. Another one is called a bottom-up approach. That means we are building up like Lego. So this is what we call adductive approach. We add in the stuff, and then by putting pieces together make it nano dimensions. Okay, so this is bottom-up. So we basically use atomic level and all the way doing stuff useful for us in nanometers. So as you can see, top-down, we have to use different important process steps, like what we call photolithography or etching. And for photolithography, actually, this is a very mature technology, and we are still using it right now when we fabricate the transistor in your CPU for iPhone or computers. And the concept is very simple. We use the light source, and right now we're using deep UV, pretty much as 157 nanometer of the wavelength. And then we basically use a mask to block the passing through of the light to create pattern onto the substrate. And this is the silicon. Okay? And how much the silicon wafer we're using right now is 12 inch, 300 millimeter. If you look at the size, it's really that big, very big. Okay? So, the beauty of this photolithography technique is we can do stepping. That means you can do this one pattern and then move to do another pattern and then move to do another pattern and then move. So even though this is what we call beauty, because we can actually do very small dimension in a small pattern and then we do it one by one, so this is a sequential method. Okay? So actually this is not good because it's slow process. Yeah. However, with this technique, we can actually draw the pattern down to below 10 nanometers. Okay? So you can think about 10 nanometer, that's small. So 1 nanometer is 10 hydrogen atom. 10 nanometer is 100 hydrogen atoms. Right? So this is kind of the smallest dimensions that we can use this technique to write. Of course, if you write smaller features, we can use other technique. We don't use the visible or UV light, we use electron. Okay? So here we call photolithography because photo meaning the source is kind of in the UV range. But we can use electron lithography, that we can use electron as a source to write the patterns. Okay? So another technique is after we do the exposing in the photolithography, so this is exposing because it's like expose the pattern onto the substrate. Then after this, we need to develop. That means originally on the substrate, this is the silicon substrate, and this is the active material we want to create a pattern. For example, this is the oxide film. So after the UV light exposed the material region here, so this is what we call photoresist. So it's a resist, meaning this is a sacrificing layer. So after the UV radiation can expose this region, then we can use chemical method to wash away this region in the development step. So that means in the photolithography, first step we expose the pattern, and the second step we wash away the unwanted pattern. So after this, we create a pattern of photoresist that on top of my active materials. And you can think about this as in the order of 10 nanometer. And then after photolithography, we can do etching. Etching, as you can see, we remove the material. So that means in the beginning, we have a pattern create with this opening around 10 nanometer, for example. Then how we remove the active material by etching for this 10 nanometers. Then we can have two ways to doing this. One is called wet etching. Wet etching meaning using just chemistry. Then we can use different chemical method in order to wash away the material. However, as you can see, wet etching, I have unavoidably have undercuts. That means because it into different direction at the same time, because when you wash away the material go down, it also go left and right. So that's why you actually increase the feature. Okay? So this is the wet etching. So for dry etching, as you can see, it's not using chemical. We're using gas. And this very different type of gas is called plasma. Okay? So it's an ionized gas species. It's called plasma. And then with this, we can create a very sharp edge wall. And the dimension is exactly the same as the photoresist. So as you can see, you have both wet etching and dry etching. if you compare, well, etching is very easy to implement because it's a chemical method. The cost is very low. However, for the dry etching utilizing the plasma, even though the feature defined is very sharp and straight, but the cost is actually very high and also very low throughput. Okay, so that's why for using different process steps, we have to think about. Sometimes we may want wet etching, sometimes we may want dry etching. This really depends on our applications. And then after this, for bottom-up technique, we can actually use different methods to create a bottom-up. So what we talked about before, the photolithography, etching is really for top-down, for creating nanostructures. Another way to create nanostructure is the bottom-up. That means we putting Lego together, going from very small, going to larger and larger, and up to the dimensions that we want. And for the bottom-up, we can have two different typical methods. One is called gas phases. That means we're utilizing the gas phase to really make the depositions. For example, we have so-called physical vapor deposition, chemical vapor deposition, so on and so forth. And the other major type of the method is called using wet chemistry. So this is using chemical technique, for example, using hydrothermal, also thermal. Those are just using beaker, using chemistry, high pressure, and different conditions, and try to synthesize all those different molecules or particles. So here I would like to highlight how we really use the chemical vapor deposition to create nanomaterials. So this is what we so-call the chemical vapor deposition. So as you can see, first we have to define our dimensions of the material by the metal catalyst. So right now what we want to do is growing nanowires. What the nanowires mean is like a wire. However, the dimensions of the diameter of the wire is in the nanoscales. That means the diameter can be as small as a couple nanometer, 10 nanometer, or 20 nanometer. So in order to define the diameter of the nanowire, first I have to use the catalyst. So this is simple chemistry. I can easily control the dimensions of the particle by simple chemistry. And after this, I put it on the substrate. And then I flow in the source of the material. So this is all chemical vapors. And after this, the chemical vapor will diffuse into the catalyst to create a supersaturation of state. So you can think about solubility. Like if you have a beaker of water, you keep adding sugar. And then at the beginning, the sugar will dissolve into the water because it's soluble, right? And up to the point that the water cannot take any more sugar, then the sugar will start to participate out from the water, right? So here we're utilizing the same principle here. Just flowing the gas molecule will try to dissolve into the catalyst or make it soluble into the catalyst itself. So at the beginning, it can take a certain amount of the gas molecule, and after going over the solubility limits, then the material have to speak out from the catalyst, or what we call participate out from the catalyst. And this is the way how to grow the nanowires. Okay? So, and this is how what we so-called using the chemical vapor method in order to grow the nanowires in this case. And besides nanowires, of course, we can also use this technique to grow carbon nanotubes. Okay, so I think carbon nanotubes, you have heard about this terminology. And one of the beauty of carbon nanotubes is because it just uses a single layer of carbon and wrap it into the tube format. Okay, if you have only one layer, it's called single layer carbon nanotube or single wall carbon nanotube. There's only one wall. Okay, so as you can see, this is one single layer of the carbon atoms wrapped together like a tube. And basically, this is developed by a Japanese scientist. It's called Ijima. And back in 1991, he is the first one to discover this carbon nanotubes. And then the most important thing is it has a very, very strong mechanical properties. If you compare the same volume of the carbon nanotube to the amount of steel steel, everyone will think about very strong material, very tough. But actually, carbon nanotube is 10 to 100 times stronger than steel. Okay, so you can think about very lightweight because only one layer of carbon atoms, and it's very, very strong. So it turns out have a lot of applications in mechanics. And also it's very, very unique in electronics because along the carbon nanotube, the electron can run very fast. So the conductivity is very high. So it also can consider to be a metal. Okay, so that's why we are using chemical vapor deposition. We can grow all the one-dimensional structure. Why we call one-dimensional? Because this is always in the wire format, either nanowires or nanotubes. And later, even back in 2010, so this is a sad story about Ichima, because if you follow the history of Nobel Prize, the three-dimensional carbon object called buckyball, he got the Nobel Prize. The inventor for the buckyball got the Nobel Prize. And then the inventor for the two-dimensional carbon material called graphene, he also got the Nobel Prize in 2010, it's Andrew Blum. However, Professor Ichima is the inventor of the 1D carbon nanotube. It still doesn't get the Nobel Prize. So that's why every time when Professor Ichima comes out to give a public speech, then he is keep talking when he will get the Nobel Prize. Okay. By the way, if you pay attention to the Nobel Prize of Chemistry in this week, past week, you know actually 3 scientists who get the Nobel Prize in Chemistry just past week. And then the topic is very, very important. 2 scientists are good enough, and another professor is from Japan, it's called Shina, and those 2 are the father of lithium-ion battery. Okay, so you can think about lithium-ion battery. We are using it every day. And finally, Professor Kuinov is the father of lithium-ion battery, have get the Nobel Prize already. But in terms of Nobel Prize, Hong Kong is very proud because we do have a Nobel Prize in physics. This is Professor Gao Kun from Chinese University of Hong Kong. He is the inventor of optical fibers. Without that, we cannot have all those optical communications. Okay? So, talk about the graphene business. So, graphene is actually very similar like carbon nanotubes because you can think about one layer of carbon atoms wrapped along in the tubes. But graphene just open up the tubes. If you open up the tubes, it's like a 2-dimensional sheet. Okay? So that means it's just one single layer of carbon atoms connecting to each other. However, those carbon atoms are formed with very unique configuration. It's called sp2. Okay? So that means they form a honeycomb structure because if you stack along different atoms, you can actually have a different porosity. And one of the post-packed porosity is called a honeycomb. And with this, actually for graphene, and one of the important discovery for this is they have a very, very high mobility of the electrons. That means the electron can run very fast in this material. And so that's why this is considered to be a very attractive alternative for transistor materials in the future. Okay, so we'll go into the transistor material later. And if we talk about other types of nanomaterials, we can talk about quantum dots. This is one single dot in the dimensions of a couple nanometer. So that's why we call quantum dots. And somehow some researchers or some people also call nanodots. And also nanowires or quantum wires and nanobelts. So you can see this is like a bell shape. And also nanotubes, so the opening is actually hollow inside, so this is a tubes, and also nanofilms and nanograins. So all this you can see have all the terms of nano, but it do have a lots of potential applications. For example, nanograins, if you can have the nanograins in the material, you enhance the mechanical property of the material very strong. Okay? So why are we concerned about those mechanical properties? For example, we can use it in the airplane, and we want to have a very light weight of the metal, and also very strong for the airplane materials. Okay? So after we go over how we fabricate all those different types of nanomaterials and what are the main I say that transistor is one of the target applications that I'm going to talk about today. And actually, Rick have quickly mentioned this Moore's law in the past in his slides. And here I would like to take it out to talk about it in a little bit more details. So what are the Moore's law? This is not science. This is not fundamental observations, okay? So Moore, if you recall from Rick's slide, is actually, he is Gordon Moore, is a founder of Intel. So back in 1965, when he co-founded Fairchild Semiconductor and later turned into Intel, so he actually made the predictions. His prediction is saying like, every 2 years, the number of transistors in your CPU will be double. Okay? So in other words, you can think about this as like a sales strategy, convince you to change your computer every 2 years, because saying like, oh, every 2 years I should have new generation of technology, right? It turns out that prediction is actually very valid. It's valid all the way from 1965 to even today. Okay? And this is the historical plot of different CPUs. So y-axis is the number of transistors, and the x-axis is the years. So here I have to disclose my age a little bit. When I was in university, I didn't get my computer in high school time, okay? Back in my time in university, I got my first computer. This is 486. If you are old enough, you recall those are actually before Pentium chip. So 386, 486, or even maybe your father or your old friends use about 286, okay? So 486 actually has up to 1 million transistors. Okay, so this is back in the time of late 80s or early 90s. And then right now, if you purchase a iPhone newest generation, and the chip is A12 Bionic, and as Vic mentioned, it's actually close to 10 billion of transistors. So you can think about up to this is really a low first one. Okay? So this really creates a challenge because that means the dimensions of transistor will get very, very, very small. Okay? So if we talk about transistor, how does it really look like? So here, what we call is a planar field effect transistor. Planar means all the configurations of transistor is in the plane structure. Okay, so that's why we call planar. So transistor is talking about like a switch. If we are in the state 1, we have electrons to flow from the source to the drain. And when we have the state 0, so the electron just cannot flow. And how to control the state 1 or 0? We use the gate to control. Okay, so that's why we call field effect. Because we use the gate to apply the electric field, and the electric field will penetrate through the oxide up to the channel region, or what we so-called active material. And then this will give you the configuration of either 0 state or 1 state. So that's why it's called field effect transistor. As you can see it in more details, the gate is metal, and we use silicon oxide as an insulator to create a field into the active material. And we use silicon as a substrate. So silicon is a semiconductor. So this is also what we so-call metal oxide semiconductor field effect transistor. So this is called MOSFET. Okay? So only one transistor. But here I do want to emphasize a couple of dimensions. For example, gate length. That means how long the electron will run from source to drain. So this is this dimensions. And the other is oxide thickness, this dimensions. Okay? So if you purchase the CPU right now, the gate length is roughly on the order of 5 to 7 nanometer. Okay? And this is what we call the 5 to 7 nanometer technology. So as you see, two-dimensional planar structure is not good enough. Then right now, the latest development is turned into the three-dimensional structure. So this is planar structure, utilizing the gate on top to control the plane of active region here to control the electron motions. So three-dimensional structure meaning the active material is actually like a fin. It comes out. And then the gate is actually controlling in the 3 dimensions. So not just on the top, it's also control the left and right. So the entire active material will have a better control in terms of the electric field penetrations. As even further, a plane is not strong enough, we go into the nanowire format. So this is what we call gate-around field effect transistor. And even here is called a plane. So not just a nanowire, we can create different planes and to use the gate to control the different planes. So that means right now we are already transformed from using the planar structure into the 3-dimensional structure. Because the planar structure, we are not good enough to control the electrical properties of the active material there. So we have to use a 3-dimensional structure to have better control of the active material there. And here, if we talk about those scaling, then we have to talk about roadmap from the electronic industry. And this roadmap is come from Intel. And as you can see, back in 2003, we are still using planar structure. So this is exactly the structure is this one, planar structure. So that's why it's here. And at that time, the technology is called 90 nanometer technology. So you can think about the gate length roughly is about on the order of 90 nanometer. That means the dimension here is 90 nanometer. And later, up to the point for 22 nanometer technology, 2-dimensional planar structure is already not good enough. Then we turn into 3-dimensional. This is called FinFET structure. So FinFET structure is exactly this one. So we have to create a fin and use a 3-dimensional way to control the fin there. And this is the 22 nanometer technology, and this is right at the time of 2011, 2012. And up to today, we are actually having 7 nanometer right now, and we are called hyperscaling because we need to scale even the fin further. Okay? So another important roadmap is TSMC. I don't know whether you guys noticed this company, but if you are have a close friend in Taiwan, I'm sure you heard about this, because this is what we call Taiwan Semiconductor Manufacturing Company. This is the largest foundry in the world. So in the electronic business, you can think about Intel, you can think about Samsung, and those two have their own brand name because they have own products. But if you think about the fabrication of the transistor, TSMC is actually fabricating more transistor than Intel and Samsung because he is a foundry. Foundry means I am a contractor. You give me order, I fabricate the device for you. So basically, he fabricates majority of the iPhone CPU and majority of the other Intel CPU processor. Okay? So his roadmap is also very similar to Intel roadmap. So back into 40 nanometer technology is still planar structure in 2007, 2008. For stepping down to 20 nanometer, then go to the 3-dimensional fin structure. And all the way to right now, actually 5 nanometer is in productions. So in the entire world, only 3 companies right now can fabricate down to 5 nanometer. Intel, Samsung, and TSMC. Okay, so that's why in Hong Kong, if we really push our technology enough, we can actually give our design to TSMC, and TSMC can help us to fabricate all the transistors. Okay? So, what current technology 5 nanometer? 5 nanometer is right here. So as you can see, this is 2019 to 2020. And by 2020, 21, 22, we expect to have 3 nanometer technology in production in the industry. And beyond that, you can think about 2 nanometer, 1 nanometer. So that's why Wick's mentioned in his slide, we are really in the golden opportunity time to look for replacement active material for electronic devices. But up to now, there's still no consensus. Who is the winner? So that's why it's a very golden opportunity time for us, because whoever can really propose a good material and the industry adapt to that new material, wow, so those are the silicon. And then the tracks is basically using the black color, so those are the metal tracks. That means we need to use the metal to control the device on off, right? So those are the metal tracks. And if we think about those two numbers, it's a gate pitch and metal pitch. So the metal pitch is how large is the porosity of the metal. So 32 nanometer. So that means from one end here to another end here, this is only 32 nanometer. So that means 60 nanometer width is the metal, 60 nanometer is the space. And then 60 nanometer is the metal, and then 16 nanometer is the space. Okay? And here, the gate pitch, this number is gate pitch, so this is 48. So the gate is talking about this purple color, so this to this layer is only 48 nanometer. So you can think, even just the 5 nanometer technology, actually there's still some room for us to scale. But if you skip further scaling down, then may go down to even couple atoms of silicon and couple atoms of those different metals. So when you have only couple atoms, quantum mechanical tunneling will be a major challenge in all those electronic devices. Okay? So if you go to talk about the CPU, we can think about two major brands for cell phone. For example, the Apple and Samsung. Okay, so this is a public information. So in a Taiwan company, he basically construct a reverse engineering. So industry reverse engineering is very common. What we call reverse engineering is we purchase product and then we try to really take it apart and look into the design of the material. Okay. However, we are not copying that because all those are patent protected. And you know, once you have a patent protected, at least we're talking about 25 to 50 years. Okay. So how to study this is because we want to see how we can improve the design further better. Okay. So this is what we call reverse engineering. So first we dissect a A11 Bionic, and A11 is actually from iPhone 8 or 8 Plus or iPhone X. Okay, so the newer generation, of course, we have the A12. And for Samsung, then we actually can look into this particular CPU, and this 8895 is from Samsung Galaxy S8, S8 Plus, and Note 8. So here, we use so-called scanning electron microscope. So we're using electron as a source to use like a microscope. Okay, so in our laboratory, of course, we look at optical microscope, right? We're using optical light as a source. But here we're using electron. Then we can observe a very small features down to nanometer. And if you digest this two different CPU, we can see for Apple, from the bottom layer of the metal all the way to the top layer of metal, this is 1 to 11. So as you can see, here has 11 layers of different metals. Okay, so you stack 11 layers of transistor together, and of course those are not stacking independently. They need to be dependent because they are actually talking to each other to form circuits, right? And all this constitutes to 2.88 micron. Okay, so 1 micron is 10 to the power 6. 1 nano is 10 to the power 9. So if you convert into nanometer, here is 2,880 nanometer. And in this roughly 3,000 nanometer, we have 11 layers of the metal. If you look into the Samsung CPU, for the same technology, basically they are also using the thin technology. Okay, so this is the 10 nanometer technology process, and this is a 10 nanometer technology process. It also has 11 layers of the metal. And compared to the bottom to the top is about 3.2 micron. So as you can see the scaling in terms of the stacking, Apple is more aggressive than Samsung. Okay, it doesn't mean Apple is better, okay? But if you compare their performance with the previous processor, for example, A11 Bionics, is 70% faster than A10. Okay, 70% faster. If you compare Samsung, design is different, but just look at the scaling, and this gives you a taste of how does the nano transistor looks like. And all this is utilizing quantum mechanical concept. Okay, so this is very important. And right now, even actually back into this year, August 29, this is a paper published in Nature. And this is a group from MIT. They use only carbon nanotube to build the first microprocessor. Okay? And this microprocessor is only 16-bit, but it has more than 14,000 of MOS, MOS, FET, but this is carbon nanotubes. Okay? And this is the design. And you can see even just only 14,000 of those nanotubes, and it's actually quite complicated. But it demonstrates maybe carbon nanotube is the future for the alternative of the silicon. Because as I mentioned, silicon cannot be scaled further down. But carbon nanotube can be as small as 1 nanometer. And also their electron mobility is much faster in carbon nanotube compared to silicon. And at this, we are talking about on the order of 100. So this is how much room that we can still scale for further devices development. Okay? And instead of just electronic industry, another very important application of nanomaterial is energy. So, and this actually is because due to the urge of energy crisis, we have to develop renewable energy. And as you can tell, we can have wind energy, solar energy, and even the tidal energy to collect those wind to sunlight and even the motion of the ocean to give us the energy. And one of the important one that actually the economy or the society is talking more heavily is hydrogen economy. Okay, so what hydrogen economy? Hydrogen economy meaning in the future, we don't expect to use electricity as a quantity to calculate energy. We use hydrogen. That means we are not transporting the electricity anymore, because generating electricity from the conventional sources are polluting, right? And if we use totally renewable energy, for example, like solar cell, and still it's not able to sustain 100%. So one of the motivation is, for example, like the fuel cell cars, and you have the hydrogen fueling stations. So fuel cell is run on hydrogen and oxygen, and then the output is water, so it's very clean. So that's why we call zero emissions. Okay. However, hydrogen is actually very notorious. Why notorious? Because hydrogen is explosive. If you store a large amount of hydrogen, actually you store a very strong bombs. Because when it explodes, it's actually very disastrous. Okay? So one of the motivation of hydrogen economy is try to decentralize the generations of hydrogen. So right now hydrogen mostly generated by, for example, fossil fuels also. However, after you generate the hydrogen on the oil refinery plants, you need to transport the hydrogen. And during the transportation and storage, this is very, very challenging, right? Because it's explosive. So the concept is, in the long run, in the future, we want to have a hydrogen filling station everywhere, and right next to the hydrogen filling station, we can use some other technology to generate the hydrogen locally. Just generate the hydrogen there. So that's why we have so-called water splitting. Okay? So water splitting is actually not a brand new concept. I believe some high school actually using this in your laboratory. This is what we call electrolysis. Right? You put a beaker of water, you apply a few electrode, and put a power, and then you come out hydrogen gas and oxygen gas, right? So the development is how to make it very low cost. So if you recall from your textbook knowledge, the electrochemical potential to split the water is 1.2 V-volt. Okay, this is the electrochemical potential for splitting water. However, if you use 1.2 V-volt to split the water there, obviously it won't work. Because we have to have some overpotential. Overpotential means you have to experience some resistance when you split the water. Why? Because first of all, I need to put an electrode there, and then when you let the electron pass through there, and then when you create electrochemical potential, you must have some power losses. This is thermodynamic limitations. Okay? So even though I dictate all those reactions, how to split the water, but of course you can see for the hydrogen generation side, it's very simple because only require one electron at a time, or two electrons to generate one hydrogen molecule. And for oxygen, it's more challenging because you need to have 4 electrons. Okay? So that's why we have to have a lot of design into those electrodes in order to minimize the voltage we use to split the water.
Why not use iridium?
Good question. So actually right now, the electrode majority are noble metals. Iridium is one of the metals. Okay? So here is what I taught from the next slides. So right now, we need to use a lot of different catalysts to go onto the electrodes. The catalyst is trying to lower the overpotential. And this is what we basically talk about in water splitting. This is what we call volcano plot. Because it's like the volcanoes. Okay? And so this is dedicated for hydrogen generation. And as you can see, the y-axis is exchange current density. That means how much electron can produce. And the x-axis is the free energy of hydrogen absorption. And even though there's no dinosaurs to you guys, but you may think about this is the energy for the catalyst to absorb the hydrogen ion to me. And also the energy to remove the generated hydrogen gas from the catalyst. So as you can see, we want to have this energy as small as possible, right? We don't want to lose too much energy to grab the hydrogen ion to me. I don't want to have too much energy loss to really resolve the generated hydrogen gas. So that's why 0 is always better. Because I don't want to waste those energy. That means I can grab them freely, I can release them freely. This is what they mean by free energy of hydrogen absorptions. And at the same time, we want to have as large current as possible. So as you can see, those are the catalysts. Platinum, iridiums. Okay? But you can think about the cost. Okay? If you go up to look up the cost of platinum, it's even more expensive than gold. Right? So if you use it, and this is not for only small quantity, we are for large scale, right? So the cost is really an issue. Are you willing to put up that much money to split the water? So that's why, in the long run, we want to look for alternative catalysts. An entire periodic table here, and this is what we call the transition metal. They have the 3D electrons. Okay? And all those 3D electrons can be hybridized in order to create a lot of different unique electrochemical properties of the metal. So the goal is try to come up with those catalysts to replace the platinum and iridium. And of course, the challenge is how to minimize the overpotential, how to enhance the activity, and how to enhance the stability of those catalysts. And you may keep asking, hey Johnny, how does it relate to nanotechnology? Till now, I don't see term nano there, right? So in nanotechnology, the beauty is actually very, very generous. Not just come from the advantages of utilizing quantum mechanical concept. Because small, we can think, oh, quantum mechanics, microscopic world. However, when you scale down the dimensions, very small, another important factor comes up. This is what we call the surface area to volume ratio. Because when you have a ball smaller and smaller and smaller, your surface effect will be larger. Okay, so if you don't just go back home, try to do a simple calculation, get 2 balls, one is only 1 meter large and one is 10 meter large. And then calculate the ratio of surface area per volume. Okay, then you must find out the smaller ball will have larger surface area to volume ratio. And why does it matter here in electrochemistry? The reason why it matters is because when we talk about chemistry, we need surface area, because all those surface area can give us the active sites, right? If I have nanomaterial, the number of active sites goes up with the same amount of volume, with the same amount of material, and that is very attractive. So that's why in the entire catalysis industry, everyone is talking about nano right now. And this is also what we do here. And also we use nanostructure. And what we do is using nickel iron fiber from the nickel iron foam. So you can actually purchase the foam very easily from even those metal shop on the street. Okay, you can go to purchase nickel foam, iron foam, or nickel iron foams. Okay, and after we get the foams, we can do different chemical steps to create. So you see those flake nanosheet decorated onto the axils of the fibers. Okay, so those nanostructure is basically, this is the SCI image to show all those nanosheet is actually decorating on top of the fibers. And for this top two figures is talking about for oxygen generation, and the bottom two figures is talking about for hydrogen generation. Okay, so as you can see, for the oxygen generation, the rubidium oxide is the band notch catalyst. So this is the green color there. And our nanomaterial can actually perform better because of smaller number. So here, the smaller number of the slope means better performance. And if we talk about the hydrogen generation, the platinum is the benchmarking catalyst. It's right there. And our material is very close to them. Okay? So indicating one material can perform two functions for either hydrogen generation and also oxygen generation. So this is what we call bifunctional catalyst. So right now in the industry, for the hydrogen generation, we need to use platinum. For the oxygen generation, we need to use rubidium oxide. And for our development, we don't need to use these two. We just only use one nanomaterial to replace both two. And then what we can do is just using a simple 1.5 volt battery. And I can generate the water splitting already. Okay? So this is one of the record till now is the lowest overpotential that can split the water. However, still far away from 1.23 because the ideal voltage is 1.23. But still, this is already quite a good achievement to split the water by using quite low potentials. Okay? So here, instead of just energy, and other application I would like to share you guys is more for surface properties manipulation by nanomaterials. So as I mentioned, the nanomaterial have a very large surface area to volume ratio. That means the surface effect is very dominant for nanomaterials. So if I can manipulate the surface a little bit, then the entire surface property of the material can change. So for this manipulation, very simple speaking, we can think either water-like or water-dislike. So if this is water-like, we talk about this as hydrophilic. If this is water-unlike or dislike, this is hydrophobic, right? So hydrophobic surface meaning if you have a surface, if you drop the water there, you see the water droplet just slip through. It doesn't stay because it doesn't wet, okay? So, and in nature, a lot of nature actually have a nanostructure. For example, one of the nature we'll talk about here is the lotus leaves. So you think about there must be something called lotus effect. Okay? So lotus effect meaning is basically super hydrophobic. When you have the water droplet comes, it will just aggregate to form the bigger drop. It won't wet. And if the motion of the water roll around the leaves is actually doing the cleaning for the leaves. So this is also called self-cleaning. So if you can have dirt on the surface, and if you can manipulate the surface to become hydrophobic, once you have the water droplet to come, maybe because of raining out there, then you can actually roll off to clean the surface. Okay? So, and don't underestimate this effect because the lotus effect is extremely useful. For example, when we have solar cell. Right? Because when we have solar cell, we put it up on the roof for 30 years. And do you want to hire workers to clean the solar cell? Because if you have the solar cell, if you have the dot, if you have the dust cover your cell surface, then you're actually losing the active area to collect the energy. Alright? If you go to hire a workers to clean the surface, A, I'm worried the damage to a cell. B, the workers may be in a very dangerous working position because it's up on the roof. Right? However, if you can apply this surface onto the solar cell, then they can do self-cleaning. And actually applying that is very simple. For example, you can actually purchase a spray, and you spray on the windshield, the car windshield windows, and then when you have the raining, you don't need to use a window blade, then the rain will just sit through because you create hydrosolar surface. And you can actually purchase that. You can purchase it on eBay. But of course, that will have questions of how long can that effect can last. And maybe only 1 day, 2 days, right? That means you may need to apply the coating every day, right? So that's why this is one of the applications that we highly think this is potential for future applications. So instead of the cleaning, another important application is antibacterial. Okay? So for example, if we make the same oxide, titanium dioxide or silicon oxide, small enough down to the nanoscale, you can actually, those are the antibacterial agents. So a lot of clothing or a lot of detergent right now, they try to add in those nano compositions. And by principle, those actually can help to clean the material. The reason is because when the particle is small enough, they can go into the cell, into the material, and damage the metabolism. Okay? And also in certain situations, for example, in the zinc oxide or tile oxide, if you use the UV light to shine, then they actually release the reducing agent, and those are antioxidants and actually can help to kill the material. So all those is also a very important applications of using nanomaterials for antibacterial or anti-statics applications. And here, another important application is for biomedical. Okay? So if you go to visit a medical doctor, one thing that you worry a lot is, can you don't do injection to me because they feel very pain, right? However, why do you feel pain? Because the needle is very long, right? When you punch through, then it go to your dermis, and that have a lot of pain receptacles or sensors, so you will still feel the pain. If you apply the gel or the cream on your skins, because your skins is not permeable, those medications or drugs cannot diffuse through the skin to go to your blood vessels, right? So those are useless. So current technology right now, either you apply the cream or you use a needle to punch through your skin. However, if you can make the needle small enough, for example, micro scale, then you don't punch through the dermis, you only go through the epidermis. And this will not go down to the pain sensor, so you don't feel the pain. Or even, in the long run, when we have the nano needles, we can actually even just attach on a patch. And then we can apply the medication on top of the needle, or just bury it inside the needle, and then just attach to your skin, and you just carry it, go running, do exercise, and you don't feel pain, right? This is just like a patch. And this is what we talk about using nanomaterials in biomedical applications. And actually, in USA, there's a company, I don't do any advertisement for them, I don't get any penny from them, but this is kind of the company that just got the FDA approved to have the micro needle out of market. Okay, so you can purchase that. It's called those micron jet 600. So as you can see, the needle size is about 600 micron. So if you talk about 600 micron, how large is it? 0.6 mm. So you can think about, you stick a 0.6 mm needle into your skin, do you feel pain? I don't know, I haven't tried that yet. So. But in the long run, we can make it nano needle and to just stick into it, and even you don't need to stick, just a patch. Okay, so this is how we use it for biomedical applications. Okay, so then this is we compare of the nano needle And this is one of the literature report of using this nano needle into doing the drug delivery. And this is plainness. Okay? So the last application I would like to share with you guys is the environmental applications. So as you can see, when we have the nanomaterial, we can make it as a fibers. And the fiber is like a mesh. So it's like a filters. So those filters can be used, for example, to get rid of the particle. So in this research group in US, basically they use the nanofibers to create a large area mesh and to remove the PM2.5 particle. Okay? So PM2.5 particle means they have certain dimensions or size. And then what this research group do is on the window, and they actually can create a shadow mask, and those can apply with if they're fibers, and then those can remove the PM2.5 particle when they go through the mask there. So it makes your air quality in your household much cleaner and better. Okay? So all this is another very important applications of using nanomaterials for environmental usage. Okay, so with this very brief introduction with the past 40-50 minutes, hopefully I'll give the audience here an overview of what is nanotechnology and how we're utilizing this in our daily life applications. In order to close this, I would like to give an outlook. So if you think about the first industrial realizations, I will think about dimensions of the materials. It's always talk about millimeter because they at that time have a precision manufacturing of those liquid metals. And up to the second industrial revolutions, we think about as the era of micrometer. So it's 10 to the power 6, minus 6. Okay? So that's why we have microelectronics. It comes up, we have computers, and we have internet. And back in right now, I think this is really golden opportunity time for us because we are really experiencing the third era of revolutions of industry. This is the era of nanos. Okay? So when we scale down the materials to another extreme, down to nano, we do see a lot of opening applications that can really change our world. So that's why we really want the teenagers, our next generation in Hong Kong, can realize how important it is and see what is the opportunity out there. And if we can work hard enough, I'm pretty sure we can get over the challenge to get very useful technology out of the nano era. Okay? So I'll like to close to the talk, and this is the samples of the nano material that we do in our labs. For example, this is the carbon nanotube bundles, and this is the vertical aligned single side nanowires. So those can be used for different applications. And thanks for your attention.